Hello everyone, this is Shobhon and welcome to my YouTube channel where I make videos while explaining physics concepts to myself, and I hope that you find this useful at some point. If you do so, please do consider subscribing to my channel and help me grow. And the topic of today's video is going to be the first law of thermodynamics. I'm going to explain this law to myself and how it naturally leads to the second law of thermodynamics. Beginning with a common sense from our everyday life, we know that everything has a cost, right? In order for you to buy something, in order for you to spend some money, you must have that money to yourself first. So it's the same with energy. You do some work and you spend your energy by doing so. So you are not allowed to spend more energy than what you have in your energy account. So the balance in your energy account, this can increase or decrease depending on how much you earn or spend, right? Your account balance can depend on your transactions, how much is going in, how much is going out, and things like that. So you need a way to keep track of your energy balance by the calculation of your earnings and your spendings. So this is what the first law of thermodynamics is. It essentially keeps track of these changes by accounting for the energy transfer in any process. So this is what it looks like. Now don't get intimidated by the looks of it. I'm going to slowly and clearly break down every term in this equation. There are three with simplified analogies, but I might warn you here because oftentimes simplified analogies can be misleading or dangerous. So I highly recommend that you read at least more than one book on this topic to make sure that what you think you understood is what it actually is. Now let me break this equation down. So on the left side we have what you would call your energy balance. So this is your energy balance, and whenever you earn something, you earn energy, it gets added here, and whenever you spend something, you use up some of your energy, it gets subtracted from here. So this is the left hand side of this equation, and on the right side we have what you would call our transactions. So this is on the right hand side, what we essentially have is flow of energy in and out of the system. Flow of energy in and out of the system, and this can happen in two ways. One is through heat and another is through work. So now let's explain these three terms in a little bit of detail. So the ingredients, as we have said before, on the left hand side we have the delta U, which is the change in the internal energy of the system, and on the right side we have the Q, which represents heat entering the system, and we have a minus W, which is work out, that is energy transferred out of the system through work, and this work is done by this system because energy will be transferred out of the system only if the system does some work. Okay, so what is internal energy? The internal energy of a system is actually the total microscopic energy of the system, which includes the average kinetic energy with the constituents of the system. So for example, if we have a container of gas containing classical gas particles moving randomly with some velocities, so we have the average kinetic energy of the constituents, and we also have the potential energy of the constituents and the chemical bond energy, etc., etc. Now the first two, the average kinetic energy and the potential energy of the constituents, these two make up something we call the thermal energy, which actually depends upon the temperature of the system. So this is proportional to the temperature. Now for many simplified systems like the ideal gas, for example, the internal energy of an ideal gas receives contributions only from the thermal energy. So for simplified systems, you might say that the internal energy is proportional to the temperature of the system. If the temperature goes up, the internal energy goes up, and if the temperature goes down, that means the internal energy went down. Then we have the two flows of heat in and out of the system. On the right side, we have Q, that is Q is the heat flown into the system, that is heat entering the system as thermal energy. Now what is heat? Heat is basically the thermal energy transferred into the system spontaneously and solely due to a temperature difference with another object. We're going to take a look at it in detail later. And we have work out, that is work done by the system. Strictly speaking, W is work done by. Notice the emphasis on by the system. So when a system does some work, the energy leaves the system. So energy transferred out of the system when the system does some work, and by work we mean sometimes something like pushing on another object, like it might be the walls of the container, it might be some piston, it might be pushing on a gear or something. So this is work out. Now let's consider the case of energy transferred as heat. So we have two containers of ideal gas, one having a higher temperature. So let's say this has a higher temperature of T sub H. So this has a higher temperature, means it will have a greater or a larger internal energy. So we have more internal energy here. And on the right side, we have another container that has a lower temperature, so it has less internal energy. So what we mean by this is that since this has a higher temperature, that means its particles will have on an average larger kinetic energy and potential energy than the particles of this. So we have much more particles moving with faster random velocities indicated by the red particles, while we do have some particles, not very much but a few particles there with velocities lesser, smaller velocities. So essentially all the velocities are random, but on the left side, which has a more temperature, which is a hot object, so it has more particles moving with faster velocities than compared to the slow particles. On the right side, we have more slow particles and less of fast particles. So when these two objects come in thermal contact, what happens is that some amount of energy leaves the system with more more energy, that is more the hot object. So it has an amount of heat Q leaving the system and flowing into the colder object. So what happens is this system has a heat Q flown out of the system, and that amount of heat is being received by the colder object. So we say that the amount of heat leaving the system on the left is Q, and the amount of heat entering the system on the right, which initially had lower temperature, is Q. And this flow of energy from the left to the right keeps happening spontaneously until they reach what we call the thermal equilibrium, until their temperature becomes the same. Okay, so this is how energy transferred as heat happens, and we might want to take a look at this simple animation that I made. Okay, now we have energy transferred as work. Okay, so let's consider that we have a container that has a piston like wall at one end. So what happens here is that the molecules builds up pressure on this wall, and they tend to exert a force F on this wall, so the piston moves outward, so resulting in an expansion of the volume. So let's see that we have a cross-sectional area here of the container, that is A, and let's consider that initially this length was x, so the initial volume was A times x, right? This was the initial volume here, and due to the pressure building up, the force exerted on the piston, this piston moves a little distance of delta x. So now the volume expanded to become A times x plus delta x. So if we calculate the change in volume, we have this A times x plus delta x minus A times x, and what we are left with is the change in velocity as the cross-sectional area A times the delta x, and this is essentially the displacement of the piston due to the force. So if we calculate the work done, which is force times displacement, so F times the delta x, and we can substitute the value of delta x in terms of the volume change from here to here, and see that this work done essentially becomes the pressure times the change in volume. So since this system is doing work and moving a piston backwards, we say the system is expanding and it is doing some work, and it is doing the work at the expense of the energy that the system had. So by doing some positive work here, the system is losing energy, so energy is flown out of this system. And on the contrary, we might as well have energy flowing into the system by doing the opposite. Say we have a piston over here, and some external agent is pushing on the piston with a force F. So now the work done will have the same quantity, but it will be negative. So whenever we have a negative work done, that means the system there is some external agent doing some work on the system, and as a result the system's internal energy will increase. So we have these two ways of increasing or decreasing the internal energy of a system. So let's take a look at them together. So whenever we have heat entering the system, so we will have a positive Q, and the internal energy of the system will increase. And whenever we have a heat leaving the system, we will have a negative Q, and the internal energy of the system will decrease. So heat enters, Q is positive, U will increase. Heat leaves, Q will be negative and U will decrease. Next we have work done by the system. So work done by the system is what we say W is positive. So the internal energy will decrease because system is doing some work and spending up some energy. So whenever work is positive, we have a decrease in internal energy, and whenever an external agent is doing some work on the system, and then the work done by the system becomes negative and the internal energy of the system increases. So essentially in the first law, what we have something like this: the change in internal energy is equal to the energy in minus the energy out. Now you might see a little different pictures somewhere rather than the picture that I've shown you, where you have a Q plus W. So delta U equals Q plus W. So this is actually the first law of thermodynamics according to chemists. Now they'd like to change the definition of work W. So physicists tends to stick with the definition W to be the work done by the system, while chemists prefer the definition of W to be work done on this system for certain reasons that I don't want to explain in this video. But essentially this is saying exactly the same thing. The physics is exactly the same, just told in a different language. We have the delta U to be the same, that is change in the internal energy, Q the same, heat flowing into the system, and whenever we have a heat flowing out of the system, this Q becomes negative. And we have W to be work in, so energy flowing in the system when work is done on the system. So the definition of W in this case is something different. So I just wanted to tell you this briefly because you might get confused. You might see different pictures of the first law, but they're all essentially saying the same thing. And we are just going to take a look at an alternative definition of the first law. I'm just going to rewrite the equation that we had initially, that is delta U equals Q minus W. So our Q was the energy flowing into the system and our W was the work flowing out of the system. And I'm just going to bring this W over to the left side, and what we have is Q equals delta U plus W. So the way to interpret this equation is the following. Heat entering the system can be used up in two ways. You can use the heat entering the system either by increasing the internal energy of the system, or it can be used to do some work W on the environment. So the heat you receive can be used in two ways. The one is to increase the internal energy of the system, and the other one is to work on the surrounding. And let's take another definition. This will be the last one. So I rewrote the equation that I initially wrote again to write W equals Q minus delta U. So the way to interpret this equation is that to do some work you must have energy either in the form of heat receiving or entering the system, or you must have some internal energy by using which you can do work. So what this essentially says is that you can't produce work out of thin air. You must have some energy to begin with if you want to do work. So this essentially says is that there is no perpetual motion, there is no perpetual machine of the first kind. And now what is a perpetual machine of the first kind? It is a machine that produces work but needs no heat or energy source. So such a machine is not possible. So this is the end of the first law. So let's just do a quick review of what we learned. So the first law of thermodynamics is actually what it does is it dictates what processes are allowed to happen and what processes are not allowed to happen. But there is a caveat here. Not every process that is allowed to happen by the first law will happen naturally. So let's take a look at an example here. So we have two processes here. Process 1, this is where we have the natural thing that is occurring. So we have a hotter object with a higher temperature Th, and we have a colder object with a lower temperature Tc. So this object will have a higher temperature, higher internal energy, and this object will have a lower internal energy. So when they come in thermal contact, an energy Q will leave this system and will be received by the system with the lower average kinetic energy, that is this. So essentially we might see that the total energy of the two systems combined did not change. So system an energy flew out of this first hotter object minus Q, and the same energy is received by the second object which was colder. So essentially we have the total energy is still conserved. Now let's take a look at another process where we have the same two objects, the hotter objects and the colder object, but this time let's imagine that an energy Q is leaving the colder object and is flowing into the hotter object. So essentially this energy of the two systems combined still is conserved, because energy still did not change, but we never see the second process occurring, right? Like we never see energy flowing out of a colder object flowing into a higher object, right? Like imagine that you have a cold cup of coffee in a room and you were standing there. So you never see the coffee getting hotter and hotter by gaining energy from the room, while the room getting colder and colder. So this never happens. You can take a picture, imagine a picture like this. Suppose for example, if you say you jump off a boat and you have some kinetic energy. So when you drop on the water, your energy gets transferred to the water molecules that splash everywhere, transforming your energy into sound and motion and all forms of energy, right? This is process 1, and the energy is conserved because your kinetic energy is transferred into the water molecules. So this is perfectly normal. But imagine a reverse process where the splashes in the water spontaneously decide to gather together and give the same amount of energy back to you to launch you back onto a boat. Like this looks funny. The energy is still conserved because the energy leaving the splash of water is essentially the same as the energy entering into you, but the reverse process just doesn't happen, even though the conservation of energy law is perfectly happy with it. So we might see that some processes happen only in one direction, even though the energy conservation will be perfectly happy, and it does not forbid these processes from going in the reverse direction. So some processes are irreversible, and the first law of thermodynamics, which is essentially a law of energy conservation, it doesn't mind going in the reverse direction, but it just never happens naturally. So we need to explain this, so we need one further layer of restriction to account for this irreversibility of naturally occurring phenomena. So this is where the second law of thermodynamics comes from. So we must have a rule that actually forbids some processes to go in the reverse direction. So let's see the second law of thermodynamics in another video. So stay tuned for the next video and stay chill. Happy learning!